everyone, and welcome back. Today we're going to go over a very common force diagram you will find in your first year physics course. And that force diagram is called the inclined plane. First, I'm going to do a complete breakdown of this force diagram, and then I'm going to go over a few nuances about this force diagram that are very important to understand. The inclined plane. So here I have a box on an inclined plane, which is basically a slide. We have the box mass, and we have, again, this angle, which I'll label theta, and we have the coefficient of friction. Now, there's one thing I want to mention here. I'm going to say the box is sliding down the ramp. So velocity is going to be this way. It's sliding down the ramp. That's going to be important, particularly for when we're discussing force friction. Now, I'm going to start with what we always start with, which is force Earth. And force Earth always pulls downward. Force Earth equals mg. Now, my axis is now shifted. Instead of being like this, my axis is now going to be like this. So I need to break up this force because it is not perpendicular parallel to my slide, to my incline, which means I have to break up force Earth, and I need to do it like this. This force is perpendicular to the slide. This force is parallel to the slide. Move this over. Here's a right angle. So how do you get these? Well, there's something I want you to notice. Let's say theta here was 30 degrees. And if you notice, I got a little bit of a right triangle right here because this line is vertical, this line is horizontal, which would make this angle on this side here 60 degrees, which in turn would make this angle in here 30 degrees because this line again is perpendicular to our slide. So this creates a pattern. Whatever angle the incline has, this angle is going to share with it right here. So in other words, this angle is theta as well. Now, as we find these, let me reiterate what these forces are. If you sit on a slide and you were to ask someone, what pulls you down the slide? They would probably say gravity, which basically is what force Earth is. It's the gravitational force from the Earth. However, that answer is only partially correct because gravity is not trying to pull you down the slide. Gravity is trying to pull you through the slide. Of course, fortunately, the slide does not allow that to happen. The slide pushes up on the person at an angle, so the person actually, if you watch, moves off to the side as they slide downward. That's where this breakup comes into play. Force perpendicular is the force that you are pushed directly into the slide with. Looking at this force breakup, how you get it would be this hypotenuse, which is mg, times cosine of this angle, cosine theta, because this is the adjacent side. Now, what's left? What's left is force parallel. Force parallel, look at the direction, is the part that pulls you down the slide. This is the part that literally allows you to accelerate as you slide down the slide. And you would get it essentially the same way, except since it's the opposite side, it would be mg sine theta. Now, before we get into friction, there's another force we need to discuss. If this object is pushing into the slide is pushing back. And the slide is pushing back exactly in the opposite direction. This, because it is perpendicular or normal to the surface, this is force normal. How much is force normal? Well, just like if you lay the box on the desk, the Earth pushes the box into the desk pushes back. This is the same thing, except it's at an angle. So force normal equals force perpendicular here. It is mg cosine theta. Now, I want to pause here for a second because there are quite a lot of problems that just test to see if you recognize the force diagram for a ramp alone with no friction. This is it. This is it every single time. If you are given an object on an incline, this is the force diagram you should draw every single time, and then take a look at anything else the problem involves. If I stopped here, what would the net force on this object be? Well, if I break up a force, it is no longer in use. because I am now dealing with the components. So I am essentially dealing with three forces here, these two components and force normal. Force normal and force perpendicular cancel, which leaves force parallel. So if I was to make an acceleration equation, it would be force parallel over mass, net force over mass. And force parallel is the only force that did not cancel. So what if friction is involved? Okay, let's add friction. And I'm going to stick with my assumption that this is sliding down the ramp, which means I have to add a frictional force. If the velocity is down the ramp, that means the frictional force is up the ramp. Force friction would be mu times force normal. And force normal is mg cosine theta, which means if I was to finish this, my acceleration equation would be force parallel minus force friction, which would be mg sine theta minus mu mg cosine theta over the mass of the object. And again, once you get to this point, you can solve for anything that's being asked for. If I had mass, theta, and mu, all that stuff is here. I could very easily get acceleration. If it was not given mu, and I was given acceleration instead, I would just rearrange this to solve for mu. And there's one more thing I would like you to notice here. In this case, I have something in all three parts of this equation, and that is mass, which means I can divide out mass and it actually cancels here. So this equation really boils down to g sine theta minus mu g cosine theta, which means on an inclined plane, even with friction, the mass is irrelevant. And if you notice, even without friction, this part here wouldn't be part of the equation. It would be mg sine theta over mass, and the masses would cancel anyway. Now, this is important because it means you could be given an inclined plane problem and not be given the mass and still be expected to solve it. And that is because if you make a second law equation, you will see that mass cancels out in the problem. In fact, if you're ever given a situation and it looks like you need the mass, but you're not given the mass, that is usually a hint that somewhere in the math, the mass will cancel. But you will only find out if you make a second law equation for your system. I didn't bother with numbers because if you can understand what we did today and put it to use, the numbers are the easy part. So I want to take a moment and clear up a few things about what we just went over. For starters, this situation on the left is pretty much identical to what we were just discussing. Velocity is down the ramp. I have force earth, which is mg. I broke it up into its component pieces, therefore is essentially gone. Force normal and force perpendicular cancel. So the only forces I have left are force parallel and force friction. Acceleration is net force over mass, which is force parallel minus force friction over mass. Mass cancels, and I get this equation again for my acceleration down the ramp. So I want to do a side note as to why the mass cancels out of this equation, not just mathematically, physically. If you notice, all of these forces are somehow dependent on force earth. Force earth is mass times g, which is again 9.8 newtons per kilogram. If I were to double this mass, that means force earth would double. If force earth doubled, that means its component pieces would double. If its component pieces would double, including force perpendicular, that means force normal would double. And since force friction is mu times force normal, if force normal doubled, then mu would double. So if I doubled the mass or tripled the mass or quadrupled the mass, all of these forces would increase by the exact same ratio. So if I wrote down second law, acceleration is F net over mass. If I double mass, all the forces double, including the net force. So I would double the denominator and the numerator, and acceleration would not change. Therefore, I could write the acceleration equation like this, because mass will cancel out in this case every single time. What if I change the situation slightly? What if I have a person here and that person is pushing the box up the ramp? So velocity is not down the ramp anymore, it's up. Well, in order for that to be true, I would first need force person, which I'll just use FP. And force friction would no longer be up the ramp. Force friction would be down the ramp. Now, if I was to take a look at this force diagram and make an acceleration equation again, let's take a look. For starters, F net over mass, force Earth gets broken up, force normal and force perpendicular cancel again. So again, I have only forces that are parallel to my plane left. So something else that needs to be decided here that I kind of glanced over in the beginning is you want to decide what direction is positive. And most people typically prefer to have the direction of the velocity as positive. So unlike in the last one, I'm going to have up the ramp be positive this time, where when we first did it, down the ramp was positive. That means if I make an acceleration equation, it would be force person minus force friction minus force parallel over mass. And this time, since force person does not break down, mass does not cancel. And this would be my acceleration equation here. So I had positive direction up the ramp. Force person is not dependent on the mass, unlike the other forces here. So in this case, mass does not cancel in this equation. So there's one more thing I want to show you, and I'm going to use these 4 blocks to do it. Each one is on a plane. The first one's flat, the rest are inclined more and more and more and more. Each one has the exact same mass, so these force earths are the exact same length each. I'm going to start adding the forces for the incline breakup. First, I'm going to start with force perpendicular. Since this one's flat, force earth on object is force perpendicular and there's no breakup. Here, force perpendicular is about here. Force perpendicular here and force perpendicular here. Now, I'm going to add force parallel. If you notice here it's very small, here it's a little larger, here it's a little larger. Finally, I'm going to add force normal. Now there's something I want you to notice. Since force normal cancels out with force perpendicular, it is getting smaller and smaller and smaller because this angle is getting larger and larger and larger. Force perpendicular is the adjacent side. So as the angle gets bigger, the adjacent side gets smaller and the opposite side gets larger. So something you already know, the higher the incline of the slide, the higher the acceleration you're going to have. So something you already know, the larger the incline of the slide, the higher the acceleration you will have as you slide down the slide. If it's flat ground, you don't have any acceleration at all. However, if the slide has a small angle, you will have a small net force, therefore a small acceleration. As the angle gets bigger, this net force, which is force parallel, gets larger, and you will have a larger acceleration. And notice in all 4 cases, force earth does not change, but all the components do, and so does force normal. Having a fundamental understanding of how this angle relates to how these forces change if the angle increases or decreases is quite important, because one thing I didn't mention is force friction. And if you notice, since force friction is mu times force normal, as you raise the incline here, if we're talking force friction static, that means the max value of force friction static actually decreases as the angle increases, which begs the question, if this has friction on it, at what point will this block start to slide down the slide? Well, let's add a frictional force to this last one and think about that. So there's no friction needed here because there's no component trying to move it. There's a small frictional force here. The frictional force here is getting larger, and the frictional force here is getting larger because the component it is fighting is force parallel. So at what point will this block break static friction? That point is when force parallel equals force friction, static max, the limit value. So force parallel is mg sine theta. Force friction is mu mg cosine theta, because mg cosine theta is force normal. So if you were looking for, say, the coefficient of friction that would force this block to break static friction at a certain angle, well, first of all, mass cancels, g cancels, and I would get mu equals sine theta over cosine theta, which in turn would be tangent theta. So if you wanted to get the coefficient that would be needed in order to break static friction at a certain angle, this is all you would need to do. If you were given mu and you were asked at what angle would this break static friction, well, that's a very easy adjustment to make. That means theta would be inverse tangent of whatever mu is. And there you have it. So not only is having an understanding between how the angle relates to these components, but also how this angle relates to force friction as well is pretty important to know. And if you're dealing with when is static friction broken, remember that as you increase the angle, force friction parallel increases. And since force normal decreases, the max value of force friction static will decrease as well. So if force friction parallel is going up, the max value of force friction static is going down, and at some point they will meet. And when they meet, that is when static friction is broken. In the future, I'll work with you on some more advanced force diagrams. Other than that, have a good day. This is Mr. M signing off.